see this right?
Yes, we can. Looks good.
Great. So yeah, this is also part of the Tarzan project, and all the people that Karen listed are involved in this project. And I think I also saw Lee here. Lee, she is from the Royal Technological University in Sweden. She will also join the cruise. She is sort of new for Tarzan. She just started her PhD on autonomous underwater vehicles. And as Karen mentioned, there is also another ITGC project, TOR. They are geologists and they will do some drilling, and they are also very interested in the multi-beam data that we get from the Hugin AUV. So just to get you started, this is a map showing what we did back in 2019 from Palmer. This colored line, the yellow line is the ship track, and then the purple and brown line is the AUV missions that we did. And we are looking at an oceanography view. So north is upwards. The ice is here. Can you see my mouse, by the way?
Yes, we can, Anna. Yes.
Yeah, great. So an oceanographer's view of the glaciology here in this area is that here we have what is called a pinning point. So here the ice is stuck to an underwater island, and this part of the ice here doesn't move much. But to the left here we have quite rapidly moving ice. There are no big pinning points left here anymore. And that means that because this thing here moves fast and this one doesn't move, there's something called a shear zone along this red line. And back here, it's grounded ice. The red line shows where it's grounded. Okay, and so the two missions we did was in these two of these three deep troughs that you see. There are three troughs that lead in from Thwaites Trough, and then we have this one, and then we have this A sub-trough here that we never got to. So one thing that would be nice to do next season is if we can get there and do some missions in there too, to see what it looks like. And red is, the color here is temperature, and the arrows are velocity. So in this trough here, we had a quite strong inflow of warm water into the ice. And because we had the velocity and the temperature, we could estimate the heat flux, the heat transport, to 0.8 terawatts. And that is sufficient to melt 50 cubic kilometer glacial ice per year. And this is quite close actually to recent estimates of the net thinning for the entire Thwaites ice shelf. So we suspect this is a high number. We suspect either this was abnormally high when we happened to be there, or else it's sort of speeding up. And in the Western Trough, we also saw some warm water. This one in turn is sort of, there's a shallow region in the middle here. So it's like two branches off into two troughs. Both of them had warm water and an inflow near the bottom and an outflow nearer the surface. We couldn't reach all the way down to the bottom with the HCP. So what we see here is, you see the HCP data here. So we suspect it's probably even faster southward flow nearer the seabed, but we didn't observe that. Okay, and we have compared temperature, salinity, and dissolved oxygen, and from those data points we could identify water masses and so on. And we see that the water here in this trough had much more melt water than what we found here in this one. And also if you look carefully and zoom in on the deep water, we could also identify 2 different deep water masses. One that is found here in Pine Island Bay and at the deepest parts here and underneath the ice shelf in this trough. And then the other one that we found here in Thwaites Trough. And from this data, we could sort of have an educated guess maybe at the flow paths. So what new thing we found was that there is a transport of deep water from Pine Island Bay that actually makes it all the way here, past the pinning point and everything. This deep water is actually lighter than the deep water that we found further north, and that means there must be at some point somewhere here. There is probably some mixing going on, either through a plume entrainment or else overturning when the water masses meet. And then we also saw this outflow of meltwater laden ocean currents. Okay, and the SOAR gang, they were very excited about the bathymetry. We could get, this picture shows the multibeam bathymetry from the ship, and the fine scale data that you see coming out is from Hugin. So they were super excited about this new detail that we could get. Sorry. We had some problems back in 2019. The first one was that we had very bad quality on the upward looking sonar. We actually brought an upward looking multibeam, or it's not a multibeam, it's a rotating sonar, MS-1000. And the other problem was that we are not sure if we could trust the upward looking DVL because it was never tested in action. It never locked onto ice. So we didn't get any data on navigation accuracy from the upward looking DVL. And what we have done now in 2021 is that we have installed and tested a new upward looking multibeam, EM2040. It's the same type that we have mounted looking downwards. We have done some tests of our upward looking DVL, and we have also bought a new long range ADCP that we will mount looking upwards. And it has a range up to 1,000 meters. And so that one will get hopefully the whole water column. And the thing that we think might be really useful is that it also gets bottom track. So we will be able hopefully to see the ice. It's only in one track, but it can, at a safe distance, you can get one line of ice thickness. That will be useful, I think, for getting help for planning the missions ahead. And also, I think that is probably valuable data in itself for the glaciologists. Okay, I want to just show you some pictures and results. So we did most of these tests and development in Kristineberg in Sweden in February. And we had a very heavy ice year in Sweden this season, which was good for us because we could do much of this in our home backyard. And we don't have room for the container on our research vessel. It's a quite small research vessel, the old one. So we had to put blankets and heating pads and everything. It was a bit heavy work with this. And then we are here in Gullmar Fjord, and we parked the research vessel. It's not an icebreaker, but we convinced the captain that we think you're a little bit of an icebreaker, aren't you? And then he was happy to park in the ice while we ran the missions below. And these, you see these structures here in the ice, we were able to observe them in the upward looking multibeam. So that was quite interesting. And here is some data from the upward looking multibeam. This structure here going across is the Coast Guard icebreaker that ran across our experiment field once. So that is what you see there. And the vertical, you see here a structure that is not real. This is an artifact from the multibeam. It's not properly calibrated here. This is not real. The stuff that follows exactly straight up is not real. So here we have, this is depth from the multibeam, and you see these structures here, they are, so depth means thickness of ice. We have you turn it upside down and convert it, so it shows us that these structures are a little bit thicker than the rest of the ice. And you can also quite clearly see them in the backscattered data from the multibeam. I'm not sure, I don't think we will see structures exactly like this, but it's sort of promising, I think, because, I mean, this is not thick ice, it's only 10 centimeters or so, and this is mostly slush here. And it's kind of promising that you can see even these diffuse structures in the multibeam. I'm very excited to get out there and get some real ice to look at. And this is the test that we did for the navigation with the test with the upward-looking DVL. So we tried to fake an ice shelf here. So we were parked here with the ship. This is ice, and out here we had a sea node, which is an acoustic beacon that ties down. So when the AUV gets contact with this beacon, we have programmed where it is. So then it's sort of locks on to that, so that it gets a new fixed position, and the accuracy becomes better of navigation. And then we had it circling here, and then it went in near the seabed, and then it turned around, and then it went up out near the ice. And we had also lowered the range of the DVL so that it was only 15 meters, so it had bottom track when it went up in, but no ice lock. And then it turned around, and when it went out, it lost bottom track and locked only on the ice. And these are the results. We did this over and over again. We were there for 2 weeks, and the multibeam was sorted within the first few days, but this thing took time. So this is what it looked like the first try. What you see here is the standard deviation of the, so in some essence, the error, it's not quite the error. The actual error is normally smaller than this, but it's a measure of inaccuracy in the data. And this is near the C node, and here we had bottom track. And then this part here, when it just skyrockets, that's where we thought we had an ice track. And the maximum here is 160 meters. And that is after only about 10 meters of mission, 10 minutes of locking to the ice. So then when we got this back, we investigated, and then it turned out we hadn't properly enabled the upward-looking DVL. So this is what it looks like with no upward-looking DVL and no bottom lock. After 10 minutes, you have an error of nearly 200 meters, so it's lost, essentially. And then we did it again, properly switching it on. We got the same results. This went on and on. We did 10 missions with the DVL enabled, and we couldn't figure out. We tried one setting after the other. We got help from Kongsberg and so on. And in the end, we understood that there's an artificial noise program into the upward-looking DVL. And it was very hard to find. This is a safety precaution because we have an upward-looking DVL, and you don't want that to lock on the water surface, because then it can be horribly lost. So Kongsberg had programmed artificial noise into the upward-looking DVL, and it never functioned. But then after all these tests, we finally figured out how to lower that noise, and this is the results that we got after lowering the noise. So now up here is 15 meters, this blue line. So it's much better. Now the standard deviation is about 10 meters or so maximum. So that was a relief. And now we have carefully documented every step that you need to take. You have to change this parameter in many places. and hopefully it should work fine. So for the Thwaites cruise in January, February and March, we have a loose idea. Part of the plan was to have an open workshop where we look at the missions more carefully, and that hasn't happened yet. And then we also have this nearly 1 month in quarantine. So I think right now the plan is to have that workshop during quarantine while no one has anything to do. But in a sense, we will focus with the Hugin on the ice shelf front region. We won't go very far in. We're not going as far in as the AutoSub, but we will try to do useful stuffs here. So this part here is where deep water, warm deep water likely is flowing in, and that would be nice to get a look at that, if we can get in there. And the other thing is to continue along the lines that we already started and just go further in. And then maybe we will get a better view at the mixing that goes on. The new upward-looking multibeam has water column data enabled, so you can sometimes, if you're lucky, you can see thermohaline staircases and structures like that. So we are hoping that maybe we will see some interesting stuff in the ice ocean boundary layer and mixing that goes on. And then we want to go further in this second trough also to get a look at the mixing and the processes going on here. And then it would be nice to get to the third trough where we never got last time. And then these yellow little shapes here, this is where I think the tour gang would be interested to have some fine scale multibeam surveys. They are very interested in previous pinning points where you can sorry, where you can get a look at the processes that went on when this was a pinning point and the ice let go. What happened then? How exactly did the ice leave this pinning point? And you can get information like that from the fine scale multibeam. I think that was all from me. Yeah. So if there are any questions, I would be happy to answer.
Thank you very much, Anna, and on behalf of all of us, thank you very, very much for showing up today when you're clearly not feeling well and pushing through to provide that important update. And yeah, very interesting talk, I thought, in many aspects. Can I see if there's any questions around the room at this stage? Must have explained these. Oh yeah, go Karen.
I have a question, and it's something that that I suppose refers to all three of the AUVs. How close, Anna, do you think you'll be able to get to the base of the ice shelf?
When we were in Gullmar Fjord, we went 5 meters from the base, but then we knew that the ice wouldn't do any dramatic changes. I think that's the big. We are completely happy to go close, but we would like to have an idea of what it looks like so that we can plan safe missions. The problem, we have also got obstacle avoidance, so it should not run into ice. That is also tested on ice, it works. But the problem is that when it turns, when it does the avoidance maneuver, the forward-looking sonar is very narrow. It is only 10 degrees or something, or 15 degrees. So it's essentially blind when it turns. And the problem is if it runs into a corner or something, then it will smash. So if we can, for example, start with going near the seabed and having the upward-looking AGCP, then we get a track where we know what the ice does, and then we can go quite close, I think, if we can follow along that track. But that means also that we have to do 2 missions essentially in the same place, and yeah, timing will be an issue and so on.
Thank you. Yeah.
I have a question.
I don't know if the others have any, what do you, other operators, how do you see this? How close do you think you can get?
I don't think we're going to be getting particularly close, given we're looking to go quite a long way in. So we will probably be doing quite a high standoff. Our intent is to maintain bottom lock for the entire exercise. So we're probably going to look to fly of the order of about 100 meters off the bottom, and then sort of go in till we get sort of down to probably 150, 200 meters of headroom, and then turn back. That's just because we're expecting the terrain to be very lumpy and bumpy and really quite tricky. So we don't want to be too close to anything, I don't think, on this one.
And Alex, if you know, for example, if we do one mission with Hugin, where we get multi-beam data of the ice draft, so you get quite a good map, would you be happy then to get closer in that track?
Yeah, it's certainly, if we know what we're getting into, then we're much happier to go closer. We still probably wouldn't look to go, well, it depends on the terrain. If we can find a very flat area, then yes, we'd go closer, and we regularly fly the AUV sort of 10 meters off the bottom. But I think it's unlikely we're going to find the conditions appropriate for that here.
I suspect we might get an update from on what the Australian AUV will do in the next presentation, unless, Peter, you want to jump in now?
Yeah, I'll just introduce it briefly, but I think we'll mention it. I guess we're kind of middle grounding, where we're focusing probably on the seafloor, long incursions, probably not as long as Odyssey, but the plan is, and you'll hear in a second about kind of doing a phased approach, but if we get ambitious and things are going well, we may do some kind of approaches and returns from the bottom ice shelf. We've tested our vertical avoidance, and we're probably looking at getting within 50 meters of the ice. That's mainly to kind of go up, turn around, and potentially collect a water sample at that level. But probably not much closer to that. But on our early incursions, we will be running our sub-bottom upwards. So even tracking the seafloor on the initial incursions, we hope to get a rough ice profile so that we can look at subsequent missions going in with a bit of a better view.
Thanks, Peter. I was going to ask a couple of questions. Just one, Anna, that current speed you had in the Eastern Trough, where you made your main estimate of the transport in, what sort of speeds were they?
The maximum speed was 20 centimeters per second, but the more, I think the average was 10 or so, but we had speeds up to 20. And yeah.
Yeah, great. And it's fascinating that long-range ADCP, so will that be facing upwards? Is that right? So you'll be close to the bottom and then trying to get as much of the water column above you?
Yeah, that's right. And
Yeah.
then I haven't had time. We have ADCP data from our DDLs too, but they are high frequency, so they only have a range of about 100 meters or so. But I haven't been able to get that data because of time issues my side, but the data is there, and the idea is that the downward looking DDL will take care of the data below the vehicle.
Yeah, great. And it's fascinating looking at those proposed missions you have. I guess I don't know if you've come up with a name for them yet. They look like Viking helmets of some sort, where you
yeah, Viking helmets, that's good.
How far into the ice will you go on those? Do you have a sense of that yet, or is that to be determined?
So last time we went in, I think we were 3 kilometers. And I think if, for example, if we build on the previous mission, I think why not go 10 kilometers or so in? But in the regions where we haven't ever been, I think maybe we must be a little bit more conservative. The strength of Hugin, I think, is to do surveys. It's a stable platform. You get good bathymetry data, and we have good accuracy on our instruments. You can look at processes, but it's not like the AutoSub long range. It's more like for exploration. So we don't really have in mind that it will go very far. We will focus on the areas where we know there are interesting processes.
Yeah, that's great. Yeah, that's great. That's nice to see the different strengths being integrated optimally in that sense. Any other questions? Okay, great. Thanks, Anna. Well, we might